Welcome to this walkthrough of LeetCode problem number 229, majority element 2.
In this problem, we'll explore how to identify elements in an array that appear more than n/3 times. Stay tuned as we cover the problem requirements, potential approaches, and an efficient solution. The problem we're solving is to identify elements in an integer array nums that appear more than n/3 times, where n is the length of the array.
To give you some intuition, let's look at an example. If the input array is 3, 2, 3, the length of the array is 3. This means the threshold for an element to be a majority is n/3 equals 1. The number 3 appears twice, which is greater than the threshold. No other element meets this condition, so the result is 3. Here's another example.
If the input array is just 1, the length of the array is 1. The threshold for a majority element is n/3 is almost equal to 0.33. Since there's only one element, 1, it appears once, which is greater than the threshold.
Therefore, the result is 1. Now consider the input, 1, 2. The length of the array is 2, so the threshold becomes n/3 is almost equal to 0.67.
Both 1 and 2 appear exactly once, which is greater than the threshold.
As a result, the output includes both elements, 1, 2. Now let's review some broader constraints and edge cases.
The array length can vary between 1 and 5 *10⁻⁴, and elements could range from -10⁻9 to 10⁻9. Some edge cases to consider include single element arrays, like nums equals 1, which should return 1. Another edge case is arrays without majority elements, such as nums equals 1, 2, 3, which would return an empty array because no element appears more than n/3 times.
If all elements are the same, for instance nums equals 2, 2, 2, 2, 2, the result would be 2. Lastly, the algorithm must handle large inputs efficiently, up to the maximum size of 5 *10⁻⁴.
To solve problem number 229, majority element 2, we need to identify all elements in the array that occur more than n divided by 3 times.
Let's start by considering a brute force approach.
The intuition here is straightforward. For each element in the array, count how many times it occurs using a nested loop.
If that count exceeds n divided by 3, we add the element to the result while avoiding duplicates.
This method is simple to understand but highly inefficient, as it requires nested loops, resulting in a time complexity of O(n²). The space complexity, however, is O(1), as no additional data structures are needed. The major drawback is that this approach becomes impractical for larger arrays due to its quadratic time complexity, making it unsuitable for efficient problem solving. An improvement over the brute force method is the hash map approach, which leverages a dictionary to count frequencies. Here, the intuition is to process the array in a single pass to maintain a frequency count of each element in a hash map. After building the frequency map, we perform another pass to extract elements that occur more than n divided by 3 times. This approach is much more efficient, with a time complexity of O(n), as we traverse the array twice, once to build the hash map and once to extract the results. However, the space complexity is O(n), as the hash map requires additional memory proportional to the number of distinct elements. While this method is faster than the brute force approach, the extra space usage is a drawback, especially when the array contains many unique elements. A more optimized solution leverages the Boyer-Moore majority vote algorithm, adapted for this problem. The key insight here is that there can be at most 2 elements in the array that occur more than n divided by 3 times. To identify these candidates efficiently, we use 2 variables, candidate 1 and candidate 2, along with their respective counters. As we traverse the array, we update these candidates and counters. If the current element matches a candidate, we increment its counter. If a counter reaches 0, we replace the candidate with the current element. After the first pass, the algorithm identifies 2 potential candidates, but we perform a second pass to confirm that these candidates appear more than n divided by 3 times. This method achieves a time complexity of O(n), as it involves 2 linear scans, and a space complexity of O(1), as it only requires constant space to store the candidates and counters. This efficiency makes it a powerful solution to the problem. The Boyer-Moore majority vote algorithm emerges as the best strategy for this problem due to its linear time complexity and constant space usage. While the hash map approach also operates in linear time,
its additional space requirement makes it less optimal. The brute force method, although simple to implement, is far too slow for practical use. A key observation here is that there can be at most two elements that occur more than n divided by 3 times, a property that stems from dividing the array into 3 parts. The Boyer-Moore algorithm exploits this insight by efficiently tracking just 2 candidates and their counts, avoiding the need for extra memory. While slightly more complex to implement than the other methods, it strikes the best balance between time and space efficiency. For this problem, we select the Boyer-Moore majority vote algorithm as the optimal solution, offering O(n) time and O(1) space performance. The problem we're tackling is LeetCode number 229, majority element 2. Here, our goal is to identify all elements in an array that appear more than n divided by 3 times, where n is the size of the array. It's important to note that the solution must be efficient, running in linear time, O(n), and using constant space, or O(1). To solve this, there are some key insights we need to understand. First, because of the mathematical constraint, there can be at most 2 elements in the array that meet this condition. This is because if more than 2 elements each occurred more than n/3 times, their total frequency would exceed n. Second, we'll use a variation of the Boyer-Moore voting algorithm, which is typically used to find a single majority element, but with modifications, it can track 2 potential candidates. Finally, the algorithm works in 2 main stages. The first pass identifies 2 potential candidates, and the second pass validates their actual frequencies to confirm that they meet the criteria. To implement this algorithm while maintaining O(1) space complexity, we use a few variables. Specifically, we use candidate 1 and candidate 2 to store the 2 potential majority elements, and count 1 and count 2 to track their respective counts during the first pass. These variables enable us to efficiently identify and manage 2 candidates. Additionally, for the final output, we use a simple result list to store the validated majority elements. By limiting ourselves to these variables, we ensure that the algorithm meets the requirement of constant space usage, regardless of the size of the input array. The algorithm begins by initializing the variables. We set candidate 1 and candidate 2 to none since we don't have any candidates initially, and both count 1 and count 2 are set to 0. This establishes the starting point for our first pass, where we identify the potential candidates. As we iterate through the array, we handle several cases. If the current number matches candidate 1, we increment count 1. If it matches candidate 2, we increment count 2. If neither candidate is matched, we check for available space. If count 1 is 0, we assign the current number to candidate 1 and increment count 1. Similarly, if count 2 is 0, we assign the current number to candidate 2 and increment count 2. Finally, if neither candidate matches and both counts are non-zero, we decrement both count 1 and count 2. By the end of this pass, we have 2 potential candidates that may appear more than n/3 times. Once the 2 potential candidates have been identified, we move to the validation step. Here, we reset count 1 and count 2 to 0 and iterate through the array again. This time, we count the occurrences of candidate 1 and candidate 2 to determine their actual frequencies. If either candidate is found to appear more than n/3 times, we add it to the result list. Finally, we return this list as the output. In terms of complexity, the time complexity remains O(n), because we perform 2 linear passes through the array. The space complexity is O(1), as we only use a fixed number of variables, regardless of the input size. This efficient use of resources ensures that the algorithm meets the problem's constraints while delivering the correct result. To better understand how the algorithm works, let's go through an example. Consider the input array nums equals 3, 2, 3. In the first pass, we initialize candidate 1 and candidate 2 to none, and both counts to 0. As we process the array, the first number, 3, becomes candidate 1 with count 1 set to 1. The next number, 2, becomes candidate 2 with count 2 set to 1. When we encounter 3 again, we increment count 1 to 2. This completes the first pass, and our candidates are 3 and 2. In the second pass, we reset both counts to 0 and count the occurrences of the candidates. Candidate 1, which is 3, appears twice, while candidate 2, which is 2, appears once. Since only 3 occurs more than n/3 times, where n is 3, so n/3 equals 1, we add 3 to the result list. The final output is 3, which correctly identifies the majority element for this input. Here, we are implementing the Boyer-Moore voting algorithm to solve the majority element 2 problem. The goal is to find all elements in the input list, nums, that appear more than n/3 times, where n is the length of the list. First, we check if the input list is empty. If it is, we immediately return an empty list since there are no elements to process. Next, we initialize 2 candidates, candidate 1 and candidate 2, along with their respective counters, count 1 and count 2, all starting at either none or 0. The first loop iterates through the input list to determine potential majority candidates. If the current number matches one of the candidates, we increase its corresponding count. If a candidate slot is available, meaning its count is 0, we assign the current number to that candidate and set its count to 1. Otherwise, if the number matches neither candidate and both counts are non-zero, we decrement both counts. By the end of this loop, we have at most 2 potential candidates that could qualify as majority elements. Now, we move on to the second pass, where we verify the potential candidates identified in the first pass. We create an empty list called result to store the majority elements. For each candidate, we count its occurrences in the input list using the count method. If the count of a candidate is greater than n/3, we append it to the result list. Finally, we return the result list, which contains all the elements that meet the majority condition. This 2-pass approach ensures that the solution is efficient and runs in O(n) time, making it optimal for this problem. Here, we start by importing the necessary libraries and defining our solution class with a method called majorityElement. This method takes an integer array, nums, as input and returns a list of integers. The first step is to handle the edge case where the input array is null or empty. If that's the case, we simply return an empty list. Now, we proceed with the main logic. We'll use the Boyer-Moore voting algorithm in 2 passes. In the first pass, we aim to identify up to 2 potential candidates that could appear more than n/3 times in the array. To do this, we initialize 2 candidate variables, candidate 1 and candidate 2, along with their respective counters, count 1 and count 2, all set to null or 0 initially. As we iterate through the array, we update these candidates and their counts based on specific conditions. If the current number matches one of the candidates, we increment its count. If neither candidate matches but one of the counters is 0, we assign the current number to that candidate and set its count to 1. Otherwise, if both counters are non-zero and the number matches neither candidate, we decrement both counters. This ensures that candidates with insufficient support are gradually eliminated. After completing the first pass, we move to the second pass to verify the candidates we identified. Here, we initialize a result list to store the majority elements and calculate a threshold, which is the length of the array divided by 3. We also reset the counters, count 1 and count 2, to 0. Next, we iterate over the array again, this time counting how many times each candidate appears. If a number matches candidate 1, we increment count 1, and if it matches candidate 2, we increment count 2. Finally, we compare these counts to the threshold. If count 1 exceeds the threshold, we add candidate 1 to the result list. Similarly, if count 2 exceeds the threshold, we add candidate 2 to the result. At the end, we return the result list, which contains the majority elements that appear more than n/3 times in the array. Here, we are given the input array nums equals 3, 3, 4, 2, 4, 4, 2, 4, 4. The first step is to initialize our variables. We set candidate 1 and candidate 2 to none, and both count 1 and count 2 to 0. These variables will help us track the potential majority elements and their respective counts. Next, during the first pass, we iterate through the array to identify the 2 potential candidates. In the first iteration, number is 3. Since count 1 is 0, we set candidate 1 to 3 and increment count 1 to 1. On the second iteration, number is again 3, which matches candidate 1, so we increment count 1 to 2. When we encounter 4 in the next iteration, count 2 is 0, so we set candidate 2 to 4 and increment count 2 to 1. As we continue, numbers that do not match either candidate decrement both counts. For example, when number is 2, both counts are decrement. This process continues, dynamically updating the candidates and their counts based on the rules.
By the end of the first pass, candidate 1 is 4 with count 1 equals 2, and candidate 2 is 3 with count 2 equals 1.
In the second pass, we verify these candidates by counting their actual occurrences in the array.
4 appears 5 times and 3 appears 2 times. Only 4 satisfies the condition that its count is greater than len nums //3, which in this case is 9 //3 equals 3. Since 4 appears more than 3 times, it is the majority element.
Therefore, the final output for this example is 4. Now, let's look at another example. For the input nums equals 1, 1, 1, 3, 3, 2, 2, 2, we again start with initialization. We set candidate 1 and candidate 2 to none, and both count 1 and count 2 to 0. This prepares us to identify the potential majority elements in the array. In the first pass, we iterate through the array to identify the candidates. On the first iteration, number is 1. Since count 1 is 0, we set candidate 1 to 1 and increment count 1 to 1. The next 2 iterations also encounter 1, so we further increment count 1 to 2 and then 3. When we encounter 3, count 2 is 0, so we set candidate 2 to 3 and increment count 2 to 1. On the next iteration, another 3 is encountered, so we increment count 2 to 2. Next, when 2 appears, it does not match either candidate, so both counts are decrement. This happens for 2 consecutive occurrences of 2, reducing count 1 to 1 and count 2 to 0. On the final iteration, count 2 is 0, so we set candidate 2 to 2 and increment count 2 to 1. By the end of the first pass, candidate 1 is 1 with count 1 equals 1, and candidate 2 is 2 with count 2 equals 1. In the second pass, we verify these candidates by counting their occurrences in the array. 1 appears 3 times and 2 also appears 3 times. Both satisfy the condition of appearing more than len nums //3, which is 8 //3 equals 2. Therefore, both are majority elements. For the input nums equals 1, 2, 3, 4, we again start with initialization. We set candidate 1 and candidate 2 to none, and both count 1 and count 2 to 0. During the first pass, we iterate through the array to identify the candidates. On the first iteration, number is 1. Since count 1 is 0, we set candidate 1 to 1 and increment count 1 to 1. On the next iteration, number is 2. Since count 2 is 0, we set candidate 2 to 2 and increment count 2 to 1. On the third iteration, number is 3, which does not match either candidate. Therefore, both counts are decrement to 0. Finally, on the fourth iteration, number is 4. Since count 1 is 0, we set candidate 1 to 4 and increment count 1 to 1. After the first pass, candidate 1 is 4 with count 1 equals 1, and candidate 2 is 2 with count 2 equals 0. In the second pass, we verify these candidates by counting their occurrences in the array. 4 appears once, and 2 also appears once. Neither satisfies the condition of appearing more than len nums //3, which is 4 //3 equals 1. Therefore, the final output for this example is an empty array. To analyze the time complexity of this solution, we need to consider the 2 main steps involved. First, during the initial pass through the array, we use the Boyer-Moore voting algorithm to identify potential majority element candidates. This involves iterating through the array once and performing constant time operations at each step, such as updating candidate variables and their respective counters. Because we only traverse the array once in this step, the time complexity is O(n), where n is the size of the array. Next, in the second pass, we verify these candidates by counting their frequencies in the array. Since there are at most 2 candidates, we perform up to 2 full scans of the array, one for each candidate. Each of these scans takes O(n), so this step has a total time complexity of O(n), which simplifies to O(n). Combining these 2 steps, the overall time complexity of the solution is O(n) plus O(n), which equals O(n). Now, let's consider the space complexity of the algorithm.
The primary contributors to space usage are the candidate variables and their counters. Specifically, we maintain 2 candidate variables, candidate 1 and candidate 2, along with their respective counters, count 1 and count 2. These require a fixed amount of memory, regardless of the size of the input array, so they contribute a constant space complexity of O(1). Additionally, we store the result in a list that holds at most two elements, the majority elements, if they exist. This also requires constant space, O1. Since no other data structures or additional memory are used, the total space complexity of the algorithm remains constant, or O1. To put this into perspective, let's compare this optimized approach with a naive solution. In a brute force method, we would calculate the frequency of every unique element in the array. This requires two nested loops, one to iterate through all unique elements and another to count their occurrences. This results in a time complexity of O(n) squared, as counting each element takes O(n), and there can be up to O(n) unique elements. On top of that, storing frequency counts would require additional space, leading to a space complexity of O(n). In contrast, the current solution is much more efficient. It achieves a time complexity of O(n) by using two linear passes and a space complexity of O(1) by avoiding the use of additional data structures. Additionally, in terms of best, average, and worst-case scenarios, the algorithm performs consistently. In the best case, such as when the input array is empty, the algorithm terminates immediately with O(1) time. For an average-sized array of length n, two full passes result in O(n) time. And even in the worst case, the time complexity remains O(n), since the same two passes are performed. Finally, let's solidify our understanding with a mathematical proof of the algorithm's big O complexity. In the first pass, we iterate through the array once, processing each element exactly one time. Operations such as comparisons, assignments, and counter increments or decrements all take constant time. This ensures that the time complexity of the first pass is O(n). In the second pass, we calculate the frequency of up to two candidates. For each candidate, we perform a full scan of the array, which takes O(n) per candidate. Since there are at most two candidates, this step also has a time complexity of O(n), which simplifies to O(n). Adding the time taken by both passes, we get O(n) plus O(n), which equals O(n). For space complexity, the algorithm only uses a constant amount of extra memory to store two candidates, their counters, and the result list, leading to O(1). Therefore, we can conclude that this algorithm is highly efficient in both time and space usage, making it a significant improvement over the naive approach. Now let's discuss some common mistakes that students often make when tackling the majority element 2 problem. First, misunderstanding the problem's constraint is a frequent pitfall. Many assume that the majority element here follows the same rule as in majority element I, where the frequency threshold is n/2. However, in this problem, a majority element must appear more than n/3 times. This stricter threshold means that directly applying logic from the earlier problem without adjustments will lead to incorrect results. Next, we have the issue of using a hash map for counting frequencies. While this approach works, it violates the space constraint since it requires O(n) space. The problem explicitly demands optimal space usage, so relying on a hash map could result in your solution being rejected in an interview or competitive setting. Another common mistake is skipping the validation step for final candidates. Even if you use the Boyer-Moore voting algorithm to identify 2 potential majority candidates, you cannot assume they automatically satisfy the n/3 condition. You must validate their actual counts in the array to confirm they meet the requirement. Missing this critical step can lead to incorrect answers, so always double-check your candidates against the threshold. Additionally, overcomplicating the algorithm is another mistake to avoid. Some try using multiple nested loops or brute force methods, which, while potentially correct, fail to meet the O(n) time complexity requirement. This inefficiency not only violates the problem's constraints but also makes your solution less practical. Another area where mistakes happen is overlooking edge cases. For instance, small arrays with only 1 or 2 elements or arrays where no element meets the n/3 threshold are common scenarios in interviews. Failing to handle these edge cases can cause runtime errors or incorrect results. Let's also look at some key insights that can help in interviews. This problem is a generalization of the majority element problem, where the Boyer-Moore voting algorithm can be extended to handle k-majority candidates. For the n/3 case, you track 2 candidates. The algorithm achieves this by maintaining up to k1 potential candidates and adjusting their counts dynamically.
For n/3, this means tracking two candidates and decrementing their counts when encountering other elements. Remember, the validation step remains critical. Once you've identified potential candidates, you must iterate through the array again to count their actual occurrences and ensure they satisfy the n/3 condition. To stand out in interviews, focus on minimizing both space, using O(1), and time complexity, achieving O(n). This demonstrates a strong grasp of optimal algorithm design. Let's now connect this problem to some related challenges that you might encounter. For instance, in majority element, which is LeetCode number 169, you find the element that appears more than n/2 times. This is a simpler case of the Boyer-Moore voting algorithm, as it involves only one candidate. Another related problem is find all duplicates in an array, LeetCode number 442, where you identify elements appearing exactly twice. Then there's find the duplicate number, LeetCode number 287, which asks for a single duplicate in an array under specific constraints. Finally, top k frequent elements, LeetCode number 347, involves identifying the k most frequent elements in an array, which is conceptually related to frequency counting but with a broader scope. Now let's consider alternative approaches and their trade-offs. Using a hash map for counting is an intuitive option. Here, you count the frequency of each element and filter those exceeding the n/3 threshold. While this approach is simple to implement, it requires O(n) space, violating the space constraints set by the problem. On the other hand, the Boyer-Moore voting algorithm is optimal in both space, O(1), and time, O(n). It dynamically adjusts candidate counts but needs careful handling of edge cases to work correctly. Finally, let's talk about the sorting approach. In this method, you sort the array first and then count frequencies in a single pass. While this approach may feel simpler to implement, it comes with a trade-off. The time complexity increases to O(n) log n, making it less optimal than the O(n) achievable with the Boyer-Moore voting algorithm. However, it can be a viable option in scenarios where simplicity and readability are prioritized over strict optimization. By understanding these variations and their trade-offs, you can confidently choose the best approach for the problem at hand, whether in an interview or a competitive programming context. Great job making it to the end. Today, we tackled LeetCode problem number 229, majority element 2, and discussed an efficient approach using the Boyer-Moore voting algorithm. Remember, mastering such problems builds your confidence in solving frequency-based challenges. Thank you for watching, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!